Hello, everyone. It's time to get started with this next Amazon webinar. Welcome to all of you. We have people from all over the globe, as usual. We have people from North America, from Europe, from Asia, from more the Pacific area as well. So welcome, everyone, for this webinar on ozonation as a quaternary treatment. The key aspects water utilities need to know. And we have plenty of water utilities present here. So I think we have around 40 different water companies registered, which is quite a big number. Many of them are from Europe, because in Europe, a lot is going on right now when it comes to quaternary treatments, but also outside Europe. And we will touch upon that a little bit. So let's get started. I will do an introduction of myself and our team very soon. So this is the agenda, this is the menu for today. We will start with an introduction of this webinar. Then we will go to some higher level trends and needs of utilities right now. And then we will go to the applications of AMOZONE. Okay, so AMOZONE is this modeling solution we have been developing and applying throughout the last years. And how do we then use it to navigate the planning stage? And how do we use it to navigate the design stage? And we will close with some lessons learned, because we are now in the market with this solution for over 6-7 years. And we could see some patterns and some important takeaways. So this is for the last points. So these are the presenters of today. This is me on the picture here, Wim Oudenaert. I am CEO and co-founder at AMTeam. Actually, my PhD background over a decade ago was advanced oxidation and ozonation. So I have been working on advanced treatments myself, not so much anymore within the AMTeam, but still it is a topic close to my heart. And then also we have our colleagues from Italy. So our first colleague is Jessica Ianes. She is an advanced modeling engineer at AMTeam, and she also has a PhD on the topic of modeling of ozonation and advanced treatments. So quite an expertise in that area as well. And then we have Roberta. Roberta has been working with numerous customers around the globe in the last 5 years. And she has been working she was involved in nearly every single AMOZONE project we have been doing at the global scale. So quite some experience from Roberta. And then we have Giacomo, who is also quite an expert. He has been co-developing the AMOZONE model itself, and still very much involved in the R&D side and the projects with customers. So this is our team for today, and we will be touching upon different topics, all of us. So let's start with a quick introduction, one slide on AMTeam for the people that do not know us yet. So we are a modeling services and a digital twin solutions company, and we use those solutions to tackle water industry's biggest challenges. So we really try to focus our efforts on the emerging big issues, and most of them are coming to us simultaneously. So we help water utilities maximizing today, but also anticipating tomorrow. And that is easier said than done, because when you look at water treatment or wastewater treatment today, it is more complex compared to 15-20 years ago, because we just simply have to juggle way more balls, and none of these balls can fall on the ground. So it's a little bit a balancing act. For this, we use a unique model fit for purpose approach. This means we smartly combine mechanistic models of various kinds with also data-driven models of various kinds. But because of our link with the process sites, we feel we can really make the best selection and combination of those models. Our company is headquartered in Ghent in Belgium, but we work for customers all over the world, because you can see on this figure, we have been active in 23 countries, and we have been working with over 100 customers, and plenty of them are utilities around the globe in different countries. And we really, in the last 7-8 years, could work on over 150 plants. Our key solutions include full treatment plant modeling and digital twins, computational fluid dynamics only for water. So this means that the 3D modeling of systems. And then we have some dedicated solutions on advanced treatment, and that's the webinar today, AMOZONE, but also on nutrient removal, plant maximization, nitrous oxide emissions, that's AMNOXA. Because also today with, for example, the upgrade of the European directive, the Urban Wastewater Directive, this solution is also rapidly growing because you want to maximize your existing assets. This webinar will go less into the details, but the good news is if you really are interested in more the scientific or technical side of advanced treatments, you can visit our YouTube channel, and there you can find all of the previous AMOZONE webinars. And it's really a huge amount of information. So instead of watching Netflix, you maybe can watch our YouTube channel for a couple of hours if you can maintain that, because it's a lot of content. But I just wanted to mention this because it's a lot of detailed information, probably useful for people getting started on the topic. All right, let's start with some trends in advanced treatments and what are the needs of the utilities then. This figure initially comes from my PhD thesis that was completed in 2012, and it's still actually very relevant today. It all starts with some global trends such as population dynamics, uneven resources, uneven distribution of water resources, the use of emerging chemicals, and climate change. And this translates into water-related trends because most of us here today are, actually all of us today, are water professionals. And this means, it drives reuse, it drives the focus on emerging contaminants or trace organic contaminants or micropollutants. It depends on the region how we call them, but in fact, they are emerging chemicals. And throughout the last 20 years, a lot of these analytical methods were developed, and this means it's high on the public agenda as well. People are aware today, and now it's also in the regulation. There is no way back. This translates to a quest for solutions, and this means advanced water and wastewater treatments. There is no way back. This is going to continue, and of course, the shift to reuse, including also in Europe, is going to manifest more and more and more. You already see it on this graph. It's also a graph I made over 10 years ago. I tried to predict the number of full-scale ozone plants for secondary effluent treatment in the US and Europe back then, so over 10 years ago. And you can see it's quite an exponential curve. And my prediction was, 42 plants in 2025. And I did some consultation with some people in the markets, and we should not be very far from that. So we have been following quite an exponential growth. And also in the coming years, if you look at utilities, what they are thinking or planning, this exponential trend is probably to continue for a while still. So now we are around 42 plants. Probably most of them are in Europe right now. For example, Switzerland, Germany, Sweden, the Netherlands. These things are emerging. Also in Belgium, where we are right now, we have a first full-scale facility. But on the other hand, so that was reuse and final discharge. But if we only look at reuse, the Water Services Association of Australia, WASA, has published this very nice website. It's really worth going through, water360.com.au. And you can see the development of reuse projects and look at the exponential explosion we have. So it goes until, it predicts until 2040. Also in Europe, this is going to take off, no doubt, because we have some climate challenges. So interesting developments here on advanced treatments. So it will become way more than secondary treatment, of course, and biological treatments. And of course, the link with drinking water will be made more and more and more. Okay, when all that will be happening, and we need to prepare not only for some climate change, but also for some regulatory updates, we need to overcome some barriers. And when you look at advanced treatments, I'm mentioning AOP here on the slide, but it should be advanced treatments. You have the cost picture. You have also the treatment plants that are very specific. People are also not experienced in the beginning, so you need to train. You have upskilling needs. You have integration questions. So how do we integrate this advanced treatment within our pre-existing plant? But then you have concerns on byproducts. People are worried, for example, about bromates when they apply ozone. One good example is the Netherlands, where you have the most stringent limit in the whole world, 1 microgram per liter. But also in other countries, for example, Germany, Sweden, people are concerned about bromates. And then you also need to have monitoring and control mechanisms of these quite expensive technologies. So there are quite a bit of challenges here. The good news is there is experience from the past, and we will try to bring it into this webinar as well. But these are things we can really not avoid, and we have to overcome these barriers in order to have successful implementation of advanced treatments. Well, that was actually one of those major drivers of building AMOZONE, because we felt it could help the various stages of technology development and implementation. It starts from the planning stage, where AMOZONE is being applied to do virtual assessments, a screening of plants. Okay, what is the suitability of advanced treatment at this specific wastewater treatment plants? Doing it fast, without too much actual piloting or overheads. And then you can make some good decisions. And when you go to the design stage, of course, these models are being used to adequately design. And then when you go to the final operation, these models can be used, or the AMOZONE model can be used as a digital twin application for smart monitoring and control, but also the training of staff. So these 3 aspects are all application aspects of AMOZONE, and some of our customers went through all of them already, and other customers started in specific stages. But this webinar will really focus mainly on this one, the planning stage, because this is where a lot of utilities in Europe are right now, what to do or how to approach this. And also in the second stage, quite some utilities are. For example, they have built a first ozonation plant, they will build a second one, a third one, or they are in the process of building a first one. Okay, but you can see it's a globally unique solution, and we have quite a bit of references already. It isn't quite an established tool. So we work with also a lot of engineering firms in the field and technology vendors in the field with the utilities. So it's quite accepted. All right, so we will start with a poll. Let me see where the polls are. Which organization do you work for? So you can do 1 or more votes to see which audience we have in front of us in this webinar. All right, I see that 50%, 60% have voted. We are almost at 70. Yes, I will end the poll and show the results. So normally you should be seeing the results. Most of you are water utilities. And then, of course, you also have, as a second group, consulting and engineering companies, and we also work with them a lot in these projects. So yeah, they represent more than half of the audience in this webinar, but also a couple of industrial end users and technology vendors and research people. Okay, thanks for voting. There will be 2 other polls further in the webinar. But I will hand it now over to my colleague Giacomo, and Giacomo will go a little bit further on the applications of AMOZONE. So Giacomo, the floor is yours.
Thank you. All right. Well, I'll walk you through quickly some of the applications of AMOZONE. But first of all, let me introduce you to AMOZONE. So what is AMOZONE? It's a kinetic model. It's a collection, a vast collection of reactions coming from literature, which we developed and we collected over the years, adding in a modular way complexity to our kinetic model. It started as an ozonation model, a model for ozonation only, and then it grew up in more complexity, and I will show you in a little bit what is included in there in a nutshell, but how it manifests. So how it appears, then what is the result? You can see the results in a dynamic way. So through a dynamic digital twin model, where you can run long-term dynamic simulations and simulate what happens across the years or in specific seasons where you have water quality changes or operational changes affecting your tertiary or quaternary treatment, or as a design tool or design support tool, where you see in very much detail in 3D what happens in every corner of your ozonation reactor or your peroxone reactor or UV train. Right? This is more to fine-tune the design and the operation. But what are the inputs that we give to AMOZONE? That we typically receive these questions, so it's important to mention that influent data such as water quality parameters, they're important in the context of the treatment that we're going to use, are typically used as input, as well as operational parameters such as the ozone gas concentration or the ozonated gas flow or chemicals that are used. These type of data are fed to the AMOZONE model, and typically what comes out is the micropollutants removal, an estimation of the bromide formation, how much dissolved ozone I can expect this because I might be interested in disinfection as well, among others, like information on how to size your generator or your diffusers package or your injection system. Right? This is more for design. So this is in general what how you can feed and what you can expect from the AMOZONE. An application which makes it a very widely applicable tool or set of tools, because the application areas are touch both the wastewater and the drinking water, but also more industrial applications on strictly processed water. And it has different functionalities. What I was mentioning before, that we developed in a modular way the kinetic model so that we could implement different AOPs, advanced oxidation processes, within the same simulation if needed. So ozone peroxide, ozone and other advanced oxidation reactions, the integration of UV and peroxide units, and soon also activated carbon units. These functionalities allow the application at different levels. The application of the model for representing a process unit, a single process unit itself, or at the plant-wide level, replicating a series of trains, treatment trains. So having multiple process units represented with the model, ozone or the UV sites, for instance. Now, the question number 2 for you is, in which stage are you active? Right? Is it the ozone or advanced treatment technology development, right? Or is it the strategic planning of the AOP application? Are you in the design or revamping of an existing facility, or in the operation of it? Right? Or maybe something else. So let's wait for the result. Yeah, that's interesting. That's very interesting. So many in the audience are already in the design phase. Of course, as expected, many are planning and exploring the feasibility, but also not negligible the part that it's already operating such a plan. All right. Thank you very much for your input. And now the second from my side and last question. So what are your biggest concerns, right? Is it preparing for the new EU directive, so for the stringent regulation, or preparing for advanced treatment for reuse, right? Or optimizing an existing installation for byproducts and in the broader context around cost or performance. All right, I see you very fast in answering. So preparing for the EU directive, as we expected, is the main concern among everyone, right? All right, thank you very much for your commitment. Yeah, we'll guide you now through a few slides regarding the virtual piloting. Since we're talking about the planning stage, right, how to prepare for and do a feasibility study, the virtual piloting is a tool that can be used in this purpose to speed up the time to application. And here is a small example from 2 cases in which we received some questions for the potential construction of an ozonation plant, right? What is the cost estimation for this new installation? What is an estimate of the micropollutants removal that we can achieve? And what is the risk for us with this water quality of forming bromate? Right? So in this group, we have a double joint project, and we helped answering these questions by using the AMOZONE and calibrating with their real wastewater, the wastewater they wanted to treat. And we applied the virtual piloting framework for this, which is about collecting on-site data and using the water that is going to be treated to run batch calibration tests, with which we calibrated the kinetic model, and with which calibration you can run a virtual pilot. So you can scale up from your batch test in the lab to a full pilot installation. Now, this is a snapshot without going into much detail of how the batch calibration tests look like. So you have the dots, which are the measurements and the show the ozone depletion in time of a certain water, and this defines the fingerprint of a certain water, because the composition of the organic material is typical of a region, of a place, and of the industrial combination with the municipal activity, and gives a unique fingerprint of the water type and how it reacts with ozone and generates particles, and ultimately removes micropollutants, but also forms byproducts such as bromate. Now, with this calibrated model, we went through a virtual piloting exercise. The kinetic model is calibrated, and then you step into a virtual world, which will now have a sneak peek of with Jessica, with a virtual installation and an exercise showing you what happens behind the scenes of AMT.
Thank you, Giacomo. I will now introduce you to this demo of the virtual piloting. Here you can see the layout of an ozonation reactor. Here we have the 2 injection chamber where ozone is injected, and 4 contact chambers. The gas is injected in the 2 chambers with a flow controller, and then ozone is injected proportionally with a ozone to UC controller in these 2 chambers. What you can do with the virtual piloting here, you can see it's performing different scenario analysis. We can start with the base case, for example, that you can see here already when the results for the bromate, for example. And we can change different parameters that you can see here on the left. We can change the inlet water quality, like bromide, nitrite, ammonia, DOC, and also we can change like operational conditions, such as the ozone dose, but also you can choose whether to switch on or off some chambers. So we see here in the base case, the simulation running, the effluent bromate is quite low, 0.16 microgram per liter, which is lower than the limit that we cited before of 1 microgram per liter. And we see the micropollutant removal. Here you see several micropollutants. These are the ones from the EU directive, the 12. And in red, you can see the average of the 12 micropollutants. That is quite around 75% removal. So basically, we see here, in this case, we don't reach the target of the 80% removal. So something we can do is, for example, increasing the ozone dose. So now we change the ozone dose. It goes from 0.3 up to 0.7 grams of ozone per grams of DOC. And as you were seeing before, we already have an improvement in the micropollutant removal, approaching almost as an average the 90%. And what you can see as an ozone dose, for example, you can also see the milligram per liter of ozone and the overall ozone dosed in terms of mass of ozone per time. That's a typical input for the generators sizing. So that's also very useful when you are in the design phase. Something else that can change in our system is the water quality of the influent water. So, for example, the ammonia can change and it can be lower in some moments of the day. So, what happens if we have a lower ammonia? Sorry, we see here we have an increase in bromate formation. So, from 1.4 bromate that we had with the increase of the ozone dose, we now reaching more than 6 microgram per liter of bromate. And that's because ammonia plays a role in forming the complex products, and it inhibits the bromate formation. So when we have higher ammonia, we also inhibit the bromate formation. In this case, reducing the ammonia concentration, we are now forming more bromate. While in terms of micropollutants removal, we don't see any change. Something else that we can test with the virtual piloting in terms, in this case, of operating conditions instead, is like we can have maybe only one chamber active. And this is due to the fact that for the diffusers, for example, you have a minimum gas flow that you can inject per diffuser. So in this case, maybe you want to have only one injection chamber active. So you switch off your second injection chamber and you only have the first injection chamber active. And this brings a local higher ozone concentration and turns into a higher bromate formation. And also we see there's a reduction of micropollutant removal due to less contact time between ozone and the micropollutants. So in this situation where you have a very high bromate, you might want to, for example, have a reduction, a mitigation strategy for bromate. And that's the case, for example, of dosing the hydrogen peroxide. So dosing just a little bit of hydrogen peroxide, 2.5 milligram per liter, it can significantly reduce the bromate formation, as you can see here, because hydrogen peroxide reacts with ozone to form hydroxyl radicals, and it consumes ozone and stops the reaction towards the bromate formation. And at the same time, we also have a slight increase in the micropollutant removal. That's because of the reaction of these compounds with hydroxyl radicals. So that's what you can test, for example, in a scenario analysis with the different steady states scenarios. But we know that the influent is not steady. There are variations in time. So for example, you can see here, we have run a dynamic simulation. You see here the flow rate into the reactor. We have here the daily variation, and then in this period, we had a rain event. You see, we also had different DOC concentration in time. For ammonia, you see we had very quite regular variations daily, and also in this period when the rain event was present, due to the dilution of the concentrations, we had lower ammonia. So as we saw in the scenario analysis, the ammonia reduction brings to higher bromate formation, and we see in the effluent tab, we go to the bromate, we see we have peaks in bromate in correspondence of this reduction of ammonia. And what about micropollutants? You can see here we also have dynamics in the micropollutants removal, and especially in this period we saw something different. That was the rainy period where the scavenging effect of DOC and nitrite was less evident, so there was more removal by the micropollutants. So overall, that's what you can test with the virtual piloting, not only the steady state scenario analysis, but also you can assess the dynamics in your plant, and see what happens specifically with the influent that you have in your case. Now I'll pass it back on to Giacomo. Thank you.
Thank you, Jessica, for this trip around the virtual pilot. Of course, this was a specific case of a virtual pilot in which we applied the diffusers configuration. About a year later, the interesting thing is that the customer came back and they said, we went for a small exercise with a real pilot, and they shared the results. And it was nice to see how the results of the pilot they ran afterwards. They were in line with the modeling results that were produced. So that is very nice to see as a confirmation that the modeling step, the virtual piloting, is meant to be a time and cost saving step, right? Speeding up the decision making, so supporting the decision making for the assessment. In this case, specifically for 2 plants, right? Usually 5 to 6 weeks. So dramatically reducing the time to action. With basically unlimited scenario testing, so you have the whole flexibility that you want in what if scenarios, and also you have an input on what it means for direct reuse for future decision making, right? Now I think is the time. I don't know if we have time for a few questions or maybe one question.
Yes, Giacomo. Some questions came in, so it's a good moment to
very good
to go over a couple of questions. So thanks for asking a couple of questions to the audience. Of course, if you have more, don't hold back. Put them on the Q&A, and because at the end of the webinar we have another time slot for Q&A. For example, a question on the. One second, we have plenty of them, so I'm looking a little bit. For example, have you done some modeling on the ozone strong water? Giacomo, maybe that's a question for you. That's a specific question on the technology?
Yeah, correct. Indeed. So that's a very specific technology that recently emerged, or maybe not so recently, but it's very interesting for the application in some cases. It's a very similar concept to the side stream injection, but you basically created a very highly concentrated solution with ozone pre-dissolved in there. So it's very interesting in cases where you have space limitation, for instance. And we did have the chance of simulating such an application. A link to another question, what about the side stream injection that might be related a little bit to this one. Yes, we showed the example of the diffusers configuration, but side stream injection is also a virtual piloting or a design exercise that we often do. Yeah, it's very typical.
Yeah. So indeed, we have been comparing a lot of equipment. There are continuously new technologies on the market, and we try to model all of them. Maybe Roberta, a question for you. You will still come after this section, but can you say something about the energy balance? That's another question. The energy assessment.
Yes, indeed. So let's say the main energy consumption comes from the pumping, but also like the generator. So these things we can also take into account in the virtual piloting assessment. These are indeed typically important to assess when it comes to cost estimation and energy cost. So yes, indeed.
Okay. Good. Some more questions are coming on, but we can proceed. And for sure, we will have some time at the end of the webinar to go over. It's interesting questions. Thanks for that. Okay, good. So Roberta, you can stay online.
Yes.
Because you will be able to talk a little bit more to walk us through design stage. We have seen in the poll that people are also looking into design. How do you properly design? And yeah, it connects to Jessica's part, because the model you have seen of Jessica at the demo she has shown was actually the real virtual full-scale plants of these cases in Sweden. Of course, the plant was back then not built in reality yet, but they are similar models. We recycle them up to the design stage. And this is where now Roberta will make a little bit the link. So Roberta, feel free to continue.
Yes, thanks, Wim. So indeed, I'm going to present here two cases. One in the Netherlands with water utility the Dombel, and another one in the US with HRSD. So the first one is the Happert ozonation reactor in the Netherlands, and this is a smaller installation. It's about 12,000 cubic meter per day, and it's focused on micropollutant removal, so as a quaternary treatment step. And the other one, the Nansemond ozonation reactor in Virginia, is a much larger installation, around 155,000 cubic meter per day. And this is part of a bigger, of a whole potable reuse facility. So in both cases, the utilities, the Dombel and HRSD, they wanted us to support the detailed design of their installation using our CFD AMOZONE model. So we closely worked with the design teams. You can see some logos here on the slide throughout this entire process. So we applied our two-step modeling approach. So at first, both utilities went for the virtual piloting, which means the conceptual design using AMOZONE as a dynamic model. And this phase helped testing how the plant would perform under different operating conditions, different scenarios, similar to what Jessica just showed in the demo. And this phase is not strictly necessary. So we have also example of utilities which starts from the detailed design already. But however, it's quite recommended to have some initial estimation that can save time and cost from our experience. So after this conceptual design, then we moved on to the detailed design with the CFD AMOZONE that comes into play. And this part of today will focus mainly on this detailed design, the outcomes from these two cases. So for the Nansemond ozonation reactor, together with the design team, we developed a brand new or innovative reactor concept, which we named flexible design. So this reactor includes 6 cells with diffusers. And this allows 3 different operational modes: the countercurrent modes, in which the odd cells are active, the co-current mode, where the even cells are active, and also an hybrid mode, where all the cells, the diffusers, can be activated. And it's actually this hybrid configuration that was particularly interesting, and according to the model, it could reduce bromate formation by 44% compared to the standard countercurrent operation. Other expected performance for this design include the hydraulic retention time, the T10, above 5 minutes, mass transfer efficiency above 95%, and bromate below 10 micrograms per liter, which could even further reduced with the addition of hydrogen peroxide. And also trace organic compounds or micropollutants removal was as expected according to HRSD expectation for potable reuse. So this flexible design gives HRSD like a strong operational control, as they can adapt the ozone, the ozone contact according to the different operating condition, raw water quality changes, and also treatment goals. So this reactor is currently under construction. While for the second case, the Happert plant, also there we tested many different designs with the CFD AMOZONE, and in the end, the co-current design was selected as it offered a better ozone distribution in the reactor, and also lower bromate formation than the countercurrent option, so with 39% less bromate. And this plant is now operational since early this year, since the beginning of 2025, and we are now collecting the data to build the online digital twin, which will run in parallel with the real installation. And with this data that we are now collecting, we are also monitoring the mass transfer efficiency. In fact, the main concern around this co-current design, which is the very first design of this type, of this kind in the entire world, the main concern was about the mass transfer efficiency for the co-current design. And as you can see here, now we are monitoring from 3 months data, and the mass transfer efficiency is above 98%, as well as the bromate formation during this continuous operational period was below the 1 micrograms per liter, which is the target for the dongle. So based on this first implementation of this type of reactor, also several other utilities, both in the Netherlands, but also like internationally, have now decided to implement or to at least consider this co-current design as well in their ozonation reactor implementation.
Thanks, Roberta, for walking us through the design. For the people watching here that have not attended previous AMOZONE webinars, especially in our previous webinar, it was from I think around May this year. We really zoom into the design of the Hapert case. Okay, so there is a deep dive, and also Waterschap de Dommel themselves, they give an explanation on how this project went from virtual piloting over design to digital twin. Okay, so it's really worth recommending if you would be interested in it. So we didn't have a lot of time to zoom in here. So yeah, you can see that there is a mixture of models we use according to the different stages. But as AM team, we really try to integrate ourselves within the existing market landscape as such to make decision making more efficient and faster. And up until now, I must say it's really a nice collaboration we always have, either directly with the utility or we are being subcontracted by the engineering companies. So some key lessons learned based on the years of applications of AMOZONE. I have actually, for you to give you an idea here, how many cases we have done so far. I've added the estimation of the number of references per each of the designs, each of the stages. So you can see that we have assisted 17 full-scale plants in the planning stage with virtual piloting. We have actually supported the design of 13 full-scale plants, and also now we are working on 5 digital twins. That's the first one will go online very soon. Okay, for the smart operation. So based on these 3 stages, what are the key lessons that we have seen or we can learn? In the planning stage, what we have seen is that quite a bit in the past and last 10 years, wrong conclusions were made with regard to full-scale performance because of smaller scale results, either lab scale or pilot scale, that were not representative of the full scale. Because it is not so easy to have representative small-scale testing of these types of technologies. It is important because you base conclusions for the full scale on these smaller scale results. And we have seen that this is quite a risk. Another one is that also the time and the budget constraints are significant. We had time. Some countries did some investigation in the tertiary quaternary treatments, but now the regulation is coming and we will need to accelerate. So for example, we work with plenty of utilities that have built their first plants, but they are now going to scale that up across different of their treatment plants. They have done some piloting and it added a lot of value. We did virtual piloting in combination with that. But the question is, will we now do the whole similar approach for all of the facilities? Probably not. So that's also a little bit of a risk because you simply don't have the resources and the time and the budgets. And on top of that, we have seen that as well, if you do on-site testing, even though it provides a lot of confidence, the testing flexibility is an issue because you can only test for a few months, maybe 1 year at max. but you cannot test all of those scenarios you would like to. So here we think we really want to offer flexibility and efficiency. We are not going to say that we are certainly in a first plant of its kind for a utility, that we are going to completely replace piloting, but significantly reduce it. And then for further rollout over several facilities, yeah, this offers very good perspectives, of course. In the design stage, Roberta has shown that you can do a lot of proactive maximization of the performance. You avoid over design, you avoid design flaws. We have seen quite a bit of plants with poor injection, poor efficiency, dead zones that could have actually been avoided, and that led to excessive bromate formation in proportion to the ozone dose. These things can really be avoided if these tools are being used. And also process integration questions. Certainly, if we look at the other part of the new directive, there's a lot on the nutrients. Yeah, you can probably also make a lot of smart integrations of advanced treatment with the upstream biology. So yeah, looking at the plants level is also something we are now looking into a lot with a couple of utilities. So this is here we are talking about virtual process design and really the maximization of the process performance, because in the end these technologies or these assets have to really perform probably for more than 20 years. And then when it comes to final operation, an experience gap is seriously an issue. Operators are used to operate a biological treatment plant, but suddenly they have to operate an advanced treatment plant. And even before the plant is being built, some of our customers are already getting trained on the digital twin, on the virtual facility. And it really speeds up the whole training process. And of course, the monitoring is a trickier. You cannot monitor bromate in real time. You cannot monitor the removal of the individual 12 micropollutants in real time. And this is, of course, what AMOZONE offers as a soft sensor. So we are talking in that stage about smart operation and training, okay? So these are a couple of key lessons, especially these risks. We have seen them over and over again. Certainly, if you do small-scale testing, be careful, I would say, and think things through. So the combination of modeling and either lab testing or the piloting is really adding a lot of value, we have seen. Maybe you have also a question, okay, if you would like to work with us, how does that happen? Well, we have two models, two business models. We are a modeling services company. This means in the design stages and the virtual piloting, we run the virtual plant models and we provide the outcomes. And this is a very collaborative approach typically, either with the utility or also with the design partners. It includes staff training, so that's a service we offer. But when the model gets to the final destination as a digital twin, we also have another model, which is we license the model as a digital twin model. And this is what we call MaaS or model as a service. Because we plug into existing platforms, one platform we have been using a lot for AMOZONE is Sumo. And you have seen Jessica running a demo in Sumo, okay? So this is all possible. And in the digital twin stage, the staff on site also has access to the scenario capability, so they can run what-if scenarios. So these are two ways. And then, how we are contracted to utilities is either directly or either we are being subcontracted by the engineering team. Okay, so that's different ways of working. All right, so this brings us to here. That's good. We have